Hello, my name is John Morrow. I'm a professor of materials science and engineering at Penn State University. I'm a glass scientist and co-author of the textbook Fundamentals of Inorganic Glasses, author of the textbook Materials Kinetics, as well as editor-in-chief of Journal of the American Ceramic Society. But I'm here to talk to you today about an exciting new invention that has emerged from my group here at Penn State, and that is LionGlass. This is a piece of beautiful LionGlass, and this is an invention that is meant to significantly lower the carbon footprint of the glass industry. So let me share my screen and I will walk you through a brief presentation about LionGlass and why we are so excited about this new invention. So let's get started. What is the problem? The problem is that the global glass manufacturing industry produces more than 86 million tons of carbon dioxide each year. About 70 to 80% of that is from energy consumption due to the high temperatures required for melting, which are on the order of 1450 degrees Celsius. The remaining 20 to 30% of that carbon footprint is due to decomposition of carbonate batch materials. The soda lime and soda lime silicate refers to soda ash and limestone. Both of those are carbonate minerals, and when they are melted, they release carbon dioxide and convert into oxide forms in the glass. So what is LionGlass? This is Penn State's newly invented family of glass composition, named after our Nittany Lion mascot. LionGlass is a completely new family of glasses that reduces the melting and forming temperatures by about 400 degrees Celsius compared to standard soda lime glass. It also eliminates the use of carbonate batch materials. So for example, in this table here on the top, this shows the amount of gases that are evolved after melting 125 grams of soda lime silicate glass. And you can see that 125 grams of soda lime batch produces 24.1 grams of carbon dioxide that gets released just from the batch to melt conversion process. With LionGlass shown in the table on the bottom, the amount of carbon dioxide that is released from a 125-gram batch is only zero point 0.3 milligrams of carbon dioxide. So LionGlass almost completely eliminates the carbon footprint due to batch material usage. Instead, the predominant gas that gets released from LionGlass melting is water vapor. So it produces about 8.4 grams of water vapor for every 125 grams of batch. And of course, water vapor is harmless from an environmental point of view. So LionGlass reduces energy costs and carbon footprint, but another advantage is that it improves the damage resistance of the glass by about tenfold compared to soda lime silicate. The upper right plot shows the probability of a standard soda lime silicate glass cracking as a function of increased load from a Vickers diamond indenter. Where this crosses the 50% threshold, this is the crack indentation threshold of the glass, where there is a 50% probability of it cracking, and this for soda lime silicate occurs at a load of 0.1 kilograms force. Comparing now to LionGlass on the bottom right plot, we actually maxed out what we could do on our equipment here. And even at a 1 kilogram force, there was only a 25% probability of the glass cracking. So we know that LionGlass has at least a tenfold improvement in its indentation cracking threshold compared to soda lime silicate under a Vickers indenter. And this translates into improved scratch resistance, improved breakage resistance. Another advantage of the improved mechanical properties of LionGlass is that this can be traded off to enable lightweighting of glass products. So in other words, you could reduce the wall thickness of glass jars, bottles, and so on. This further reduces the carbon footprint of glass manufacturing since less energy is needed. Less batch materials are needed. It also improves manufacturing throughput, and it improves the downstream costs and environmental impact from transportation if you have lighter weight products. One final advantage of LionGlass is that it also improves ultraviolet absorption compared to soda lime silicate. So if glass is being used as a packaging to store anything that's sensitive to UV radiation, whether it's a food, beverage, cosmetic product, this can provide some extra advantage there. Now, LionGlass is available in its clear form, as shown here. We also have many different colors of LionGlass. This is a cobalt blue. This is a copper aquatic blue. This is a pink, which is an erbium doped version of LionGlass. All these different colors are available. And so LionGlass also makes a really interesting artistic medium. It's safer for an artist to use because the temperatures are shifted so much lower. Also, LionGlass doesn't have a really bright glow compared to soda lime silicate. So when an artist is working on soda lime silicate, they generally need to wear dark safety glasses to protect their eyes from all the radiation that's being emitted. And with LionGlass, the temperatures are shifted so much lower that that is no longer an issue. LionGlass is meant to be a drop-in replacement for soda lime products for use as architectural windows, automotive glazing, packaging for food, for bottles, for cosmetics, tableware. These would be the glass articles that you drink out of. Anywhere, any place where soda lime silicate is used, LionGlass could be a potential replacement, and also bring the benefits of lightweighting. From a manufacturing point of view, this is meant as a drop-in replacement where the temperatures would need to be adjusted to shift all the processing conditions downward in temperature to match the viscosity of soda lime silicate manufacturing. The intellectual property for LionGlass is covered under a patent application, low melting glass compositions, articles, and methods of making the same, which was filed on March 14th, 2023. We have also filed a second provisional patent application, which is still not publicly disclosed. So we would need to have non-disclosure agreements in place to discuss any of that. But this patent and the second patent cover both novel family of glass compositions, articles made using LionGlass compositions, and methods for producing LionGlass. And a key thing is that the research that led to this patent was conducted only using internal Penn State funds, so we have no obligations to any outside sponsors. The team is shown here. So I am the principal investigator for the team. As I mentioned, I'm Dorothy Pate Enright, Professor of Materials Science and Engineering, also a member of the U.S. National Academy of Engineering and the National Academy of Inventors, with 80 granted U.S. patents to my name so far. My team is shown here, my current team. The experimental efforts in the lab are being led by my postdoc, Dr. Nicholas Clark. He started in my group here at Penn State as an undergraduate student, completed his PhD in my group, and now is continuing as a postdoc. And he's doing an outstanding job leading the glass melting efforts, characterization, and helping out so much with company interactions. We also have three wonderful undergraduate students working with us. Julia, Elizabeth, and Josette are all doing a great job and making outstanding contributions in the lab. So I'm very fortunate here to have this great team. We've also been working with a company in the Netherlands called Celsian. They have a wonderful setup for actually taking movies of the glass melting process and measuring the gases that get evolved during the glass melting process. This shows a photograph of their setup where this is their furnace with their transparent window shown here, a video camera to see the batch to melt conversion process, and then this is connected to a gas chromatographer to measure the concentrations of gases that are being released. So if we start here with a standard soda lime silicate glass, on the right, this shows a movie of the batch to melt conversion process, where in the upper left part of the movie, this shows the current temperature in degrees Celsius. So we are approaching 650 and now getting close to 700 degrees Celsius, and you really can't see anything visually happening yet. On the left-hand side, the plot here shows the concentrations of gases that are being released as a function of temperature. You can see that by far the dominant gas that gets released is carbon dioxide. The dark blue curve here shows the concentration of carbon dioxide divided by 100 just to fit it on the same scale as everything else on this curve. So as shown at the beginning of this presentation, if you integrate this curve, you get the total amount of carbon dioxide that gets released, which for a 125-gram batch is about 24 grams of carbon dioxide. The remaining gases that get released later are due to the fining process. Sodium sulfate is used as the fining agent here, so we have some release of both oxygen as well as SO2. Now, looking over here on the right-hand side back at the movie, we're getting to 1200 degrees C. You can see a lot of the batch reactions are taking place. Carbon dioxide has been released, but there's still a lot more that needs to happen with respect to obtaining a good quality homogeneous melt. So now we're getting to 1350 degrees C. You can see more bubbling that starts to take place. As we get to 1400 degrees C now, you can see the fining agents are kicking in. We get a foaming behavior as more gases are released. The gases rise to the top. They're creating a nice homogeneous mixture. Now we're at 1500 degrees C, and this calms down. And for this crucible, when we get to about 1525 degrees C, that's when all the gases have been released, and there's a nice high-quality homogeneous soda-lime melt here at the bottom. Let us compare that now to LionGlass. This video is a little bit out of focus at low temperatures, but it will come in focus a bit later. So let's look first at the gas chromatography results on the left. This shows the concentrations of gases being released as a function of temperature. And first thing to note is that the CO2 concentration is no longer divided by 100. This is the actual CO2 concentration, and it is below 100 ppm across the entire range of temperatures. So if you integrate all of this, it's just a fraction of a milligram of carbon dioxide that is being measured. This is due to any trace impurities of carbonates that happen to be in the batch, as well as atmospheric carbon dioxide that was measured. Instead of CO2, the dominant gas that gets released is water vapor, H2O. The green curve here shows the measured water vapor divided by 1,000. So this, if you integrate this, the 125-gram batch produces a little over 8 grams of water vapor that gets released. So from an environmental point of view, that is highly preferable compared to the release of carbon dioxide. The other peak that you'll note is the SO2 peak. We did include a small amount of sodium sulfate here as the fining agent and found that that works as an effective fining agent as it does in soda lime silicate. And the key thing is that the SO2 is released at much lower temperatures. So it actually works quite well even at the lower temperatures of LionGlass. Now, if we shift our attention back to the movie on the right, we just hit 700 degrees C. And if you look, you can already start to see some of the batch reactions taking place. You can see the melting process takes place in stages as the lower melting temperature components melt first, then they react with other constituents of the batch. They form lower melting eutectics, and so this melting process occurs as in progression. And you can also see gases being released here, mostly water vapor is being released because some of these batch materials are hydrated with either chemisorbed or physisorbed water. The water is going to escape here. We're getting to 860 degrees C. As we approach 900 degrees C, the behavior here is very similar to what you saw at around 1400 degrees C in soda lime silicate. Now we are at 925 degrees C, and a lot of this fining process is finishing up. As we get to 950 degrees C, the gases have been mostly removed, and we're obtaining a really high quality homogeneous melt here at temperatures, in this case, shifted down by more than 500 degrees Celsius compared to soda lime silicate. So that is a huge advantage in melting. If you have any questions about this, feel free to reach out to me or leave any questions in the comments. I may not be able to answer them. Some of them could only be answered under a non-disclosure agreement, so please be aware about that. And you're also welcome to check out this article that was featured on BBC News. So thank you so much for watching, and I hope that you share my excitement here about LionGlass. Thank you.